Hello everyone. Today we are going to cover the Terzaghi bearing capacity formula, how to find out the bearing capacity equation given by Terzaghi. So, theoretical equation given by Terzaghi, broadly known as Terzaghi bearing capacity theory. So here, according to Terzaghi's, if you want to find out the bearing capacity equation, you can take a shallow foundation and that should be a continuous foundation. So a foundation which is resting over this soil, the foundation is going to be a strip or continuous footing. This footing is going to rest over this soil and it is at shallow depth. So if you are going to have, say this is the shallow footing embedded into the ground, this is the strip footing or continuous footing, and if the load is transferred and it increases and goes to the ultimate condition, so what is known as the ultimate bearing capacity, the soil below this will go under shear failure. So there is going to be a case of limiting equilibrium. Limiting equilibrium. That means when the ultimate load is applied over the foundation, the soil below this, the foundation soil, goes under shear failure. So here below the footing, when this is the intensity of the loading, QU is ultimate bearing capacity, and I have already defined what is ultimate bearing capacity in my previous slide, that when you apply the ultimate loading that induces a shear failure, that loading is called the ultimate bearing capacity. So here this is the footing, and at the base of the foundation, this we can draw a horizontal line. So here Terzaghi's famous bearing capacity equation, that we are going to derive it. So the size of the footing, let's say the width of the footing, this is strip footing is B, and the depth of the foundation is DF. So it's a shallow foundation. So there are certain assumptions, and those assumptions given by Terzaghi you must remember. So what are the assumptions? The first assumption is the footing is going to be a continuous or a strip footing. So first assumption is the footing is continuous or strip footing. So it is a case of, therefore it is a plane strain condition. The second assumption is this footing is at shallow depth. The footing is at shallow depth. So shallow foundation. What is shallow depth? That you already know it. That is the width of the foundation here, or the depth of the foundation is going to be less than equal to the width of the foundation. That is, the depth of foundation upon the width of the foundation is going to be less than 1. So that is the second assumption about the foundation. The third foundation is, the third assumptions is the soil below the base of the footing. This is the base of the footing. Base of the footing. So soil below the base of the footing undergoes shear failure. So the soil below the base of the footing undergoes general shear failure. General shear failure. Last slide I have told you what is general shear failure. That is the SPT number, capital N, should be greater than equal to 30, and the failure strength should be less than 5%, and the ground is going to be dense. That means the relative density RD should be greater than equal to 70%, and the value of phi, that shear parameters, should be greater than equal to 36 degree. So 3 assumptions. The fourth assumption, that the soil below the base of the footing is uniform up to very deep depth, and it is homogeneous. So the fourth assumption that you can, the fourth assumption is soil below the base of the footing is homogeneous and uniform up to great depth. So it is going to be an isotropic medium, isn't it? Homogeneous, and it is going to be uniform up to great depth. Also in this assumption that the shear failure is going to be below the base of the footing, and it extends up to the base of the footing. The shear failure which is general shear failure is up to the horizontal surface below the base of the footing. below the footing's base. Right? So that is another assumption. And it doesn't extend beyond this, it terminates over here. That means this, according to this assumption, what will happen? You can see here that the footing and below the base of the footing there is the shear zone. There is a shear zone that's going to develop. This is the zone 1, this is the zone 2, and this is the zone 3. Zone 1 is in under elastic equilibrium. And zone 2 is under passive equilibrium and known as zone of radial shear. And zone 3 is known as zone of linear shear. So there are 3 zones. So there is in passive zones, passive equilibrium, and this is in elastic equilibrium. That means this is going to be the part of the footing, zone 1, and it moves along with the footing, and there is no strain over here. So if you consider this kind of shear failure, it doesn't extend beyond the base of the footing. So there is the horizontal plane below the base of the footing, and the shear line doesn't extend up to the surface. It terminates over here, according to Terzaghi's bearing capacity theory. And the soil above this horizontal surface, if the unit weight is gamma and the depth of the footing is df, so this is replaced by a surcharge. So here, at this horizontal plane, the surcharge Q equal to gamma times depth of the footing. So this is called, this surcharge is called gamma times df, where gamma is the unit weight of the soil mass and df is the depth of the footing. So this is what is the shear failure that's going to develop in the soil mass if you are going to have the ultimate bearing capacity or ultimate intensity of loading if you are going to apply it, QU. And also the surface, you can see here, how is this surface? Ground level is going to be horizontal. So another assumption given by Terzaghi is the ground surface is horizontal. This is also. So these are 6 assumptions that's given by Terzaghi. Based on this, he has developed his theory known as Terzaghi bearing capacity theory. So here, if I take this zone 1, so if I take this zone 1, there is the elastic zone and that moves with the base of the footing. So here you will find that this is in elastic equilibrium and this is in passive equilibrium. So therefore here there is going to be the cohesion force will come into picture, and this cohesion force, capital C, is if I call it A, B, D, so capital C will be the cohesion parameter C multiplied by AD. Here also the capital C, this force, is going to be equal to cohesion parameter C multiplied by BD. So this is going to act, and also here the passive pressure is going to act, and that passive pressure, so PP, and here the passive pressure on this, because this is pushing this side. Zone 1 is pushing, so there will be resistance offered by zone 2 and zone 3 here, because you are trying to push it. So here there is going to be the cohesive force, capital C, equal to a small c into AD, and there will be a passive force, PP. This passive force with the perpendicular to this surface is making an angle phi. So and this angle is going to be tan this 45 minus phi by 2, and this is also, this angle is going to be phi. So this angle is going to be phi. So this is perpendicular to this surface, and this is going to be perpendicular. So this angle is with the perpendicular. This is going to be angle phi. So this is also 45 minus phi by 2. So these are the three zones: zone 1, zone 2, zone 3, zone of linear shear, zone of radial shear, and zone of elastic equilibrium. So that is how the forces are coming into picture. Now you will see that QU is the ultimate intensity of loading. So the ultimate, therefore, ultimate bearing capacity according to Terzaghi will be the ultimate bearing capacity multiplied by B into 1, that is B must be equal to, because it is a continuous footing, so QU into B must be equal to, what are the forces? So these are 2 times PP acting in the vertical direction, so 2 times the passive force that is going to come into picture, plus this is a component, you can find it out, 2 times C into this angle is phi, so this will be sin phi, the vertical component of C, so 2 times capital C into sin phi, and this weight is acting in the downward direction because it is pushing, it's coming with the foundation itself in the downward direction, as if this elastic wedge which I am showing over here, this elastic wedge is the part of the foundation itself, and therefore there will be minus sign. Minus 1 by 4, you can find out the area of this very simple way, gamma B square into tan phi. So you find out the area of this, find out the volume of this, multiply it with gamma, So that's the vertical force that's going to be in the downward direction, and the magnitude is going to be this. This is how the basic derivation given by Terzaghi. So way back, he has given this equation. This is the basic equation that everybody should know about it. Now this part, the PP, now here also, the unit cohesion, if you take it, and if you can find out this AD and DB, then you can substitute it in terms of B. This is going to be the width of the footing, so you can find out in terms of B. So you can simplify it, and this PP can be written, so this PP can be written like this. So what he has given is the ultimate bearing capacity QU into B equal to 2 times passive force plus 2 times C sin phi minus 1 by 4 gamma B square into tan phi. How it has come, I have already explained with the help of the elastic wedge. Now, this PP is due to PP gamma, so it is due to the psi, which is going to be cohesionless. C is going to be 0, and it's a weightless mass and without considering the surcharge. So that is going to be PP gamma plus this, if you consider the cohesion without considering the surcharge, it is going to be this passive pressure due to cohesion, and you can also consider this passive force due to this surcharge Q. So this is PPQ. So this can be written like this, plus the rest of the quantities here you can put it. And if you simplify everything, these are all you can simplify it further, and if you simplify it, the final expression on simplification for that, what you get is the ultimate bearing capacity of a strip footing or a continuous footing for general shear failure is given by small c and c, where c is the shear parameters c and phi, plus surcharge q and q, plus 0.5 times gamma b n gamma. This is the famous Terzaghi bearing capacity equation. This is the famous Terzaghi bearing capacity. Now this NC, NQ and N gamma are called bearing capacity factors. These are called bearing capacity factors. These bearing capacity factors are the function of phi. So shear parameters C and phi. So these are all functions of phi. And Terzaghi has plotted a chart for various value of phi. You can get the value of NC, NQ and gamma. So he has given in the tabular form as well as in the chart form, and you can finally find out the ultimate bearing capacity of the foundation. So please remember it. For general shear failure, QU equal to C NC plus Q NQ plus 0.5 gamma p n gamma, where Q is the surcharge, So Q is the surcharge equal to gamma times dF. So this is his surcharge, gamma times dF. You can remember it. Also, if it is a cohesive, purely cohesive soil, this is for C5 soil. So here the soil is C5 soil. It has both cohesion and phi value. But if it is a purely cohesive soil, so for purely cohesive soil, remember this equation, the ultimate bearing capacity, and for purely cohesive soil or saturated cohesive soil, then the value of phi under undrained condition, that is phi u equal to 0, and therefore for phi u equal to 0, this implies that the value of NC given by Terzaghi is 5.7 and NQ equal to 1. These are all functions of phi, bearing capacity factors. It is known as bearing capacity factors. So these bearing capacity factors for phi u equal to 0 is given by Terzaghi as 5.7 and NQ equal to 1. Therefore, for purely cohesive soil, Qu will be equal to C into NC, that is 5.7 times cohesion C plus QNQ. NQ is 1, so plus Q. And therefore, if you want to find out the net ultimate bearing capacity, the symbol is Q, Nu is going to be equal to 5.7 times C, because you are going to remove the surcharge in net ultimate bearing capacity. So these expressions must be remembered, and this is for general shear failure and for continuous footing. So if it is local shear failure, if soil is not dense, it doesn't meet the criteria, and it's a local shear failure, then this equation needs to be modified. So general equation given by Terzaghi must be modified. So how will you modify it? That I will tell you. If the soil, foundation soil, fails in local shear, so it is not general shear, it is local shear. That means the soil is medium dense, and you know, for medium dense, Terzaghi has said that the phi will be less than equal to 28 degree. For general shear, it will be more than 36 degree, and here the phi will be less than equal to 28 degree, and n value I have already explained to you will be lesser. So for medium dense, if that's the case, local shear failure, then you will have to modify Cn phi and then substitute in the equation. So what is the modified value of Cn phi? Cn is the modified value of C. So C becomes Cn, and modified value of C will be 2/3 of C. And tan phi equal to this modified value will be equal to 2/3 of tan phi. So phi m equal to tan inverse 2/3 of tan phi. And for that phi m value, you can find out from the Terzaghi chart or Terzaghi table, you can find out the value of NC, NQ, N gamma. These are the bearing capacity factors, and then you can substitute in the general equation number 1. So what is the general equation number 1? QU equal to CNC plus Q NQ plus 0.5 times gamma B N gamma. So here this value of C will be modified, so it becomes 2/3 of C, so this becomes Cm into NC, and for the modified value of phi m you will have to take NC, NQ, N gamma for general shear failure. Or if you take the value of phi directly, then you will have to, in the chart or in the tabular form, he has given also the bearing capacity factor for local shear failure. So for local shear failure, it is given like this. You can make it like this. So now the equation becomes QU equal to 2/3 of C NC plus Q NQ plus 0.5 gamma B N gamma, and these NC, NQ and N gamma are the function of this modified value of phi. So if phi is 30 degree, you can modify it to phi m, and then for that in the general shear failure you can find out NC, NQ and gamma. If you take it phi, then this becomes equal to 2/3 of C NC prime, where NC prime is corresponding to the value phi. Phi, this is for local shear failure, plus Q NQ prime plus 0.5 gamma B N gamma prime. These are where these are all function of phi, and these are all for local shear failure. So in the tabular form, Terzaghi has given all these values. So the limitation, if you see Terzaghi's bearing capacity theory, he has derived it for which type of footing? For a strip footing, for continuous footing, and not for if it is of some other shape. In the next slide, I will tell you how the bearing capacity theory or bearing capacity equation has been modified for different shapes. If the shape is going to be a square or if it is going to be circular, how you can modify it, and that we will see in the next slide. Thank you.